Well, reciprocity theorem of mutual inductance. We have seen that the mutual inductance between two inductors remains the same irrespective of primary current passed through any of the two inductors. Already we have seen. Now we can prove this reciprocity theorem in two ways, as by vector potential methods and other by virtual work methods. The vector potential method, which generally we say as Newman formula. If you see to the picture, here we have C1, C2 are the two contours carrying current I1, I2, and DL1, DL2 are the differential length elements. R1, R2 are the position vector of these length elements with respect to certain origin O. When current is passed through, let us say, the primary current in contour C1, so in that case magnetic field B1 must be produced. We say that B1 is the field due to flow of current I1 in contour C1. And if you see that when this magnetic field is produced, you recalling that divergence of B is always 0. So therefore here the field which is produced by the contour C1, it will have a divergence of B1 equal to 0, and which will be associated with certain vector potential A1 such that the field vector B1 vector must be equal to curl of A1 vectors, and here A1 vector we name as vector potential due to the field B1, magnetic field B1. Now the total flux linked with the contour C2, in that case the flux which is realized by the contour C2 is produced due to the current I1 which is flowing in the contour C1. Now in that case, if this is the total flux linked with C2, which we can name as phi 21, that can be written as surface integral S2 capital B1 vector dot ds2 vector, differential surface elements, that must be equal to the surface integral of curl of A1 vector dot ds2, because our B1 vector is expressible as curl of A1 vector. Now this S2 is the surface integration over the contour C2 which is enclosing, and therefore the phi 21 can be written as surface integral S2 curl of A1 dot ds2 can be equal to contour closed contour integral A1 vector dot dl vector, because we can always change by using Stokes theorem surface to line integrations, we can always change. So therefore here the surface integral of curl of A1 dot ds2 has been changed over to A1 vector dot dl2 vector, where L2 is the length element, and we have changed here surface ds2 to length dl2. Now here A1 vector, which is the vector potential to the corresponding field B1, is nothing but mu 0 by 4 pi closed contour integral over C1 I1 times dl1 vector by modulus of R2 vector minus R1 vector. This is, if you recall the discussions of the vector potentials, how we can write in a current carrying loop. So if you substitute here A1, then the phi 21 must be equal to mu 0 by 4 pi closed contour integral C2, and again closed contour integral of C1, substituting A1 vector, that is I1 times BL1 open modulus of R2 vector minus R1 vector times whole times dot DL2 vectors, and that must be equal to mu 0 I1 by 4 pi times closed contour integral C2 closed contour integral C1 dl1 vector dot dl2 vector open modulus of R2 vector minus R1 vector. And if you compare this expression, this phi to 1, which this expression if you compare to equal to capital M21 times I1, then your mutual inductance with subscript M21 can be written as mu 0 by 4 pi closed contour integral C2 closed contour integral C1 of dl1 vector dot dl2 vector open R2 vector minus R1 vector mod, and this is the Newman formula for M we have seen. In the same manner, we can consider the loop C2, which if current is allowed to primary current instead of I1, if you allow primary current in I2, in the same manner we can proceed to find that there will be a magnetic field B2 which is produced during the flow of current I2 in the contour C2. And in that case, we can also see that the divergence of B2 being 0, so B2 vector can always be written as curl of A2 vectors, where our A2 vector is the vector potential corresponding to the field B2, and this vector potential A2 can be written as mu0 by 4 pi closed contour integral over C2 I2 dl2 by modulus of R1 vector minus R2 vector. So if you now see that the total flux linked with C1 coil, which is due to the current flowing I2 in the C2 loop, that is equal to phi 12 can be written as surface integral of B2 dot ds1 vector, and this can always be written by Stokes theorem, that surface to line we can write as phi 12, which will be equal to curl of A2 dot ds1 must be written as closed contour integral C1 A2 vector dot dl1 vector, and our A2 vector is nothing but mu0 by 4 pi I2 dl2 vector upon modulus of R1 minus R2 vectors. So therefore we can compare with phi 12 with M12 I2 to write that the mutual inductance coefficient M12, which can be written equal to mu0 by 4 pi closed contour integral C1 closed contour integral C2 dl2 dot dl1 vector upon modulus of R1 vector minus R2 vector. Now if you compare these two, M21 and M12, subject to condition to check that dl1 dot dl2 is same as dl2 dot dl1, and R1 modulus of R1 vector minus R2 vector is same as modulus of R2 minus R1 vector. So therefore our M21 is same as that of your M12, which we say as M, that is the coefficient of mutual inductance, and hence it ensures that the mutual inductance between the two inductors remains the same. It is immaterial in which component the current is flowing in a primary to begin with. In the same way, we can also proceed to prove this theorem by virtual work methods, which is an application of scalar triple product. You can say that in that case, if you see to the same figure again, where you check that induced EMF in C2, which is due to the current I1 in the contour C1, we can write it equal to EMF 12, which is equal to minus M21 times di1 by dt, where M21 is the mutual inductance of C2 with respect to C1, and this induced EMF E12 will cause I2 in secondary coil, of course, and consequently will again induced in C1. That is, induced EMF in C1 can again be written as E21 must be equal to minus of M12 times di2 by dt, where M12 is mutual inductance of coil C1 with respect to C2. The force on the differential length element dl2, which is carrying the current I2, which is placed again in the field B1 created by the current flowing in C1, can be equal to delta F1, that is equal to I2 times cross product of dl2 vector cross B1, that is recalling the F equal to IL cross B, the magnetic force. Now this force we can generate a virtual work, we can say, that is delta W2, which is the work done in displacing this length element dl2 by a distance, let us say delta r, can be written as delta F1 dot delta r. That will be equal to I2 times dl2 cross B1 vector dot delta r. So that will be equal to I2 times delta phi 21, where phi 21 is the flux within the volume of the parallelepiped with sides dl2 vector, b1 vector and delta r vectors. So therefore our total work done in bringing this C2 from infinitive to the present location can be assigned to equal to W2, that must be equal to integration of dw, which we can write as integration of, that is I2 times delta phi 21, and if you integrate this delta phi 21, that will be equal to I2 times phi 21. So where our phi 21 is the total flux linked with the coil C1, and in a similar manner you can pick up the coil C2 as the primary, where we can find out that the total work done in bringing C1 from infinite to the present locations equal to W1, which is integrations of dW1, that is equal to I1 times delta phi 12, which can be on integrations I1 times phi 12. Now with phi 12 is the total flux linked with coil C2, and since the final positions in both the cases are equivalent, so therefore the W1 and W2 in both the cases are same. If you substitute for W1 as I1 times phi 12, and for W2 if you substitute I2 times phi 21, and again recalling the NEWMANN'S formula which we have discussed, that is phi 12, which is equal to M12 times I2, and phi 21 is equal to M21 times I1. We can replace this phi 12 and phi 21 with M12 times I2 and M21 times I1. So therefore our W1 equal to W2 can be again rewritten as I1 times M12 times I2, which must equal to I2 times M21 times I1. And here if you compare both the sides, then in that case obviously M12 is equal to M21, let us say it as equal to M capital M. So this is how we can prove the reciprocity theorem of mutual inductance, ensuring that the current in any of the components to begin with is immaterials. And we can check the validity of this theorem by applying to concentric coils, coaxial solenoids and other cases which we have already seen. We will have more discussion regarding these and problems in our subsequent class.